All right. So today we will talk about how to compare two systems. So first thing we talk about is sample versus population. It turns out we have already discussed that previously, so that might be a repeat. But then we really want to get on to confidence interval and then comparing systems by confidence interval visually using confidence intervals. And so the rest of it is all about different confidence intervals, and then sample size for determining means and proportion. That says that how big samples do you need, okay? And that applies to measurement as well as simulations. So sample is came from the French, as I said before. A sample, it means example, and that means an example is not a definite statement. All right, that means it is a best guess. That means there is a probability of being right and probability of being wrong based upon that example, right? And so that's what we are going to talk about. What is the probability of being right and what is the probability of being wrong? So if you generate several million random numbers with mean mu and a standard deviation sigma, and from those millions you take n observations, let's say 100 observations, the sample mean will not be equal to mu, guaranteed almost. There is some chance that it might be equal to mu, but the sample mean of 100 observations, even though you generated it correctly from a distribution whose mean was mu, but the sample mean will not be equal to mu. So sample mean is not the same as population mean, and population mean is unknown. In most of the situations, we don't know what the population mean is, and so we use the letter Greek letters for that. As I said before, Greek is kind of difficult, right, as compared to English, which we use for the sample. So the sample is easy to get, and we use English letters for those. So if you take k samples, so you have million numbers, and you took one sample of 100. Now starting one sample, you take 2 samples, 3 samples, 4 samples. As you increase more and more samples, you will get more and more sample means. And so now what you can do is, based upon these, you somehow want to put some bounds of probability being wrong or right. So we put 2 bounds, C1 and C2. And we say, well, based upon whatever I know so far, the probability of being wrong is 5%, but 95% chance is that I am, the population mean is in this area, in this range. Okay? So that is what is called confidence interval. Basically, the probability of being wrong is alpha, that is called the significance level, and generally that is either 0.05, which means 5%, or 0.1, which means 10%. R could be 0.0001, means you want to be really 99.999% sure, which is often be used. For example, when we design our networks, the probability of a data getting wrong to you is 10⁻⁶. That means actually it is 6/9 is very common. So 10⁻⁷. And that is actually not the probability of data being wrong. That is the probability of data. It could be as much as 10⁻12 in some cases, in some situations, in some applications. So we are, that probability of being wrong could be any extreme small value. As I said before, we might use just 5% or 10% as a common value. And so when you say 5%, you want to be, when you say 10%, you want to be 5% wrong on this side and 5% wrong on that side, and you want 90% to be this area. When we say 10% error, then significance level is 0.1. Alpha is 0.1. Your confidence level is just 1 minus that. So confidence level is 90.9 times 100. Generally we say in percentile. So we say 90% confident. That means probability of my being correct is 0.9. Okay? And so basically, all we want to do is we want to get 2 bounds. C1 and C2 such that given whatever we know so far, we are sure that the mu lies in that range. So we'll present a formula here and then we'll show you what the formula is based upon. So let's say you want to get 90% confidence interval, then you want to have 5% error on this side, 5% error on that side, and we know that the means are normally distributed. Why are the means normally distributed? Anybody remembers the theorem? Yeah, central limit theorem. Central limit theorem says that regardless of what the original observations are distributed with, when you take many of them and you add them together, the means are normally distributed. So the sample mean is normally distributed, and therefore if you take a lot of sample means, they will have this distribution. Okay? And so we want to find out this 0.05 point and the 0.95 points, which you can go into the table. And so you go to the table and find what we call Z 1 minus alpha by 2. Z means unit normal. Unit normal means 0 mean and 1 standard deviation of 1. So we go to the table and Z sub 1 minus alpha by 2. Why 1 minus alpha by 2? Because if alpha is 0.1, then alpha by 2 is 0.05, and 1 minus 0.05 is 0.95. And so, so we find out that, and since it is basically a normal distribution, it is symmetrical around the 0, standard normal. So whatever is on this side, the same value minus same value happens on the other side. So this is minus Z sub 1 minus alpha by 2, and this is plus Z sub 1 minus alpha by 2. These two values are basically plus and minus, right? So we take whatever we measured, x bar minus Z multiplied by s upon square root of n, and comma x bar plus Z multiplied by s upon square root of n, and that gives me some range with which we can be confident that 90% chance that the actual mean, the population mean, is in this range. Now, there are a few multipliers here, let's understand those two. So one thing we understood is that the sample mean is normally distributed because central limit theorem told us so. However, there are two more things. One is that since this sample came from that distribution, it really is normally distributed with mean of mu. So that is one thing we know. Second thing is we found the standard deviation, and if the sample standard deviation is then basically sigma upon square root of n. So why is that? So sigma is the standard deviation of the original population. If you take one observation, two observations, you will find that their standard deviation is sigma, right? However, when you add those things together, the variance goes down, and as you add more and more and more, you will not. I mean, actually, this is a simple thing about adding normal variables. If they were all normal, you can very easily show that if you had one normally distributed samples or observations, you take one observation, it will have a standard deviation of sigma. You take two observations, you add them up, their variance will be equal to 2 sigma. Their variance will be equal to sigma square by 2, and so its standard deviation will be sigma divided by square root of 2. When you take 3, square root of 3, and so on and so forth. So when you take n, the mean will, so basically the sample mean has the mean of mu and the standard deviation of sigma upon square root of n. As n goes up, this standard deviation goes down. What that means is that this width of this graph, width of this curve goes down and down and goes thinner, and the curve becomes thinner and thinner, more peakier and peakier and peakier. If you take infinite observation, then you can be very sure that the sample mean is same as the population mean. And that is the advantage of taking many more samples, because as you take the samples, more and more samples, your variance goes down, your variability goes down of the sample mean itself, and then you can be more and more sure about the population mean. And so basically, mu we don't know, but we know that x bar is 90% chance that it is between this value mu minus this and mu plus that, and therefore we think that the mu is in this range. So here's an example. Let's say x bar of 32 observations, x bar is 3.90 and s is 0.95, which is the sample standard deviation. So we put that 3.90 minus plus s upon square root of n, and this is the z value. How did this come about? We go to the book and we have to read. You read it on table A2. On table A2.95, you read under the row which says 0.95 and the column which says 0000. Everybody found the page 629? Yeah? So there in that column, in that row, it says 1.645. And why we read the first column? Because we want 0.950. The first column is for 0. If you want 0.951, you read the second column. 0.95 to third column and so on and so forth. So 1.645 is the z value for a normal unit normal distribution, so that it reaches 0.95 at that value. And since we want 90% confidence interval, we are reading the 0.95, 95. Why 95? Because you're not only that, because you want 5% error on this side and we want 5% on the other side. Even the total error is 10%, so we want 90% confidence interval, but we read 0.95. Right, 1.645. Now, those of us who do this all the time, we remember this number 1.645 because it is such a common thing. And however, in the real world, what will happen is you will not always be doing 90%. You might be doing some other confidence interval. And so you will have to read, get a table and things like that, right? And so anyway, so with that 1.645, if you put that number, then we get the range 3.62 to 4.17. So that is the range. So basically based upon these 32 observations, all we can say is that the real population mean is in this range, and we could still be 10% wrong. And suppose you want a 95% confidence interval, not 90%. Right? So then you have to read the table. Can you read the table now and find out what number to use on the table? For 95%, what are we reading first of all? 0.975. So 0.975, how do you read 0.975? What row and what column? So the row is 0.97 and the column is 6th column. Right? And there it says 1.960. First thing you should notice is that which one is wider, the 95% or 90%? So basically, I am sure 90% sure that this is the range, but if you want to be 95% sure, then this is the range. If you want to be 99% sure, then this is the range. The more surety you want, more confused I am, basically in terms of I have a bigger width I have to give you. You understand? If I wanted to be just 10% sure, then basically it would be I can be very sure that it is close to 3.90, maybe plus minus a little bit. All right. So as we increase the confidence level, the interval increases. All right. So 99% confidence. Similarly, for 99% confidence interval, what do we read on the table? Yeah, 995. So let's see how do we read that value. So we go to the table and read 995. So we go to the 995, actually it turns out to be the first column of that row, which is 995. Everybody sees that? It is in the first column, not the 6th column, I think it's in the first column. Alright, so we put that and now it comes out even wider. It was something like it was so now it is even wider than that. So 99% confidence interval is even wider than 99 and 95, and that is wider than 90 and so on. So do you feel comfortable that you can Get the confidence interval? So the meaning is that whatever interval I specify, I would be right 90% of the time and wrong 10% of the time. If I take one sample, based upon that sample, I will come up with a confidence interval which goes this wide. Right? And we will say that the mean is in this range. If I take another sample, obviously my confidence interval will be totally different. So with this other sample, I will say that I expect that the real mean, population mean is in this range. With the third sample, could be different, fourth sample, fifth sample. If you do it 100 times, you would be wrong some of the times, like this. But you'll be right how many times? 90% of the time, or whatever you are talking about here. So when you say confidence interval, you are 90% sure, so you could still be wrong 10% of the time. All right, so for small samples. Now, here's the thing. Basically, the way all this confidence interval thing worked is because we assumed that we have a large number of observations. That means we have a large sample, and therefore the mean is normally distributed. If we don't have a large, and by the way, large sample is defined as 30. Okay, that's not absolute boundary. If you have 29, it won't be normal, and 31, it will be normal. No, that is just for most of the time. That is how it works out. There could be exceptions where the distribution is so weird that with 30 observations it is nowhere close to normal. It can happen. Okay? But without any further considerations, if you didn't have any more data, then you will say, well, 30 observations will make it generally normal. And so it will apply to any distribution. However, if you don't have 30 observations, then what do you do? One thing you could do is you will say, well, I really don't know then, because obviously the mean is not normally distributed. But if you make one more assumption, then it becomes a solvable problem. The second assumption you make is that if we assume that the observations themselves are normally distributed, then the problem becomes simple because then, you know, the 2 and 3 and so on and so forth remain normal. So the mean would be normally distributed, but the standard deviation part, which we didn't discuss before, and I would right now not go into detail, is that then the sums of the normals are normal, but the sums of the squares of the normals have a distribution called chi-square, and based upon that, you know, if you go into the ratios and all that, you will come out that really the standard deviation multiplier, this thing that we had z, will now have a t distribution. And this will become clear actually by the time we reach chapter 29. So those of you who are interested could go to chapter 29 and read it there. But right now it is too advanced for me to, you know, jump to that place. Let me see chapter 29. So in chapter 20, page 497, there is something called students' t distribution. So that is where it describes what t distribution is all about, and it shows that t distribution is the ratio of normal to square root of chi-square and so on and so forth. And so based upon all that observation, you can say that basically, since this is what is S, if your observations are normally distributed, then the way you calculate sample variance is you square the observations and then you add them up. So the sum of the squares of the normal is chi-squared. Then you take a square root. And so things like that. So basically when you do that, it turns out that this is the formula, t distribution. So the key thing to notice at this point is that not only that you cannot use z, use t. The second thing to notice is that this makes two assumptions. One, that you have, the additional assumption you are making now is that the observations themselves are normally distributed, which was not the assumptions we had made before. If with that assumption we can do it for small samples, however, this t distribution has two parameters. For different values of n, the t value is different. So the second parameter is, you have to read at n minus 1 what we call degrees of freedom. You have to read that, and the confidence interval is 1, and what we call significance is alpha by 2, and the confidence is 1 minus alpha by 2. So now you have to read in the table. So we are going to read the table with t distribution, which is on page 631, table A.4. In table A.4, when you read it, it has two rows. One is the probability, second is the degree of freedom, and the table goes, for n equal to different values. All right. Okay. So once you realize that instead of z you have to use t, then you get the confidence interval as before. So here is an example. This is a small sample. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 maybe, right? 7, 8 observations. 8 observations. So the sampling mean is 0. Sample standard deviation is 0.138. And so for the 90% confidence interval, we have to read 0.95, and n minus 1 is 7. So 0.95 and 7. So we go to that table, and then we read the 7th row. You see, even though there are 8 observations, it says n, but really here in the table, n means the degree of freedom, which actually is 7. Okay? So don't confuse that n with the number of observations. When you're doing here, the number of observations is 8. But when you're reading here, it is n minus 1. You have to read degrees of freedom. So, and I don't know if anybody remembers why n minus 1 degrees of freedom are left when you do standard deviation. You are taking the sample mean. If you calculated the standard deviation using sample mean, then you use n minus 1. If you calculated the standard deviation using population mean, which you, by some chance you might know, then you use n, right? But so that is the reason. So the same reason. So basically, so here we have n minus 1 degrees of freedom, 7 degrees of freedom, and we want confidence of 0.95 for 90%, and therefore we read 0.95 and 7. So if we go there, that is the 7th row, and the column number 1, 2, 3, 4, 5th column. And then the 5th column, it says 1.895. So 0 plus minus, minus plus 1.895 times s. Oh, that's another thing, is that we don't have a square root of n here. So it's typo only in the slide, not in the book. In the book we have it correct. So basically I need to put here 0.138 divided by square root of 8. So here also 0.262 divided by square root of 8. All right. So some of you already know confidence intervals and you know this part, but what is less commonly known and is more important is to visually check things out. So whenever you plot the confidence intervals, generally what you do is you put a dot at the sample mean, and you just draw a line which width is equal to the confidence values, right? Now we can do several things with this though. If the zero line crosses the confidence interval, that means that the population mean could be 0. If the zero line does not cross the confidence interval, then you could be very sure that the population mean is non-zero. And similarly here, in these two cases, you could be 90% sure, or whatever number you used for the confidence, you can be sure that the population mean is non-zero. Here you are kind of not sure, and so you could say, well, given the data that I have, based upon that, it could as well be 0, right? And this is a very powerful observation. Why? Because now you can distinguish a 0 from non-zero, in the sense that you can distinguish whether this number is really has any what we call significance or importance, or or things like that. Okay, so let's see. So we measure two processors, and the difference in the processor time comes out this. This is the difference. So we basically take the mean. The mean is 1.03, and so most people will make a big deal about this 1.03 and say, look, this processor is better than the other. right? But if you do it right ways, then what you will do is you will say sample size is 7, and therefore we can use the P formula, 1.03 minus plus T. Now we need to read at 6 degrees of freedom, and let's say we want to read 99 percentile. This is 99. This one is 99% confidence, right? So we read 0.995 value from the table, and that value comes out to be 1. Where is the value? Is 3.707. So we multiply 1.03 minus plus 3.707 star 1.6, which is the standard deviation, divided by square root of n. If you do that, you get the 99% confidence interval is minus 1.21 to 3.27. Now, given this data, what will you say about the difference in the two processors? There is no difference, because there could be 0. The difference could be 0, because this interval includes 0. So now, the important thing is that whenever you see a confidence interval, you look at these numbers, and without doing too much mathematics, too much statistics, too much probability theory or hypothesis testing or whatever, you can see the numbers right there, and minus and plus means that includes a 0, means as good as 0. If you were to do a very strict hypothetical test, many of the books have a hypothesis testing section, statistical books. And so what will happen is with 99%, you do the hypothesis testing, the hypothesis will fail in the sense that the difference is 0. Basically, the same answer you can get without doing any of those statistic things, just looking at the two numbers and seeing if the signs are different. If the signs are different, then regardless of what those numbers are, it includes a 0, and therefore the difference is 0, as good as 0 actually, and at that confidence level. Now what can you do? So we did 99%, and now it includes a 0 here. What I have to do? I have to say, well, at 99%, I think this difference is not there. But if you want to be error of 10%, the confidence interval narrows down. At some point, the 0 will be out. When the 0 is out, then you can say, well, if you want 80%, then yeah, the difference is maybe non-zero. But I could be around 20% in that case. Opposite signs means that we cannot say with 99% confidence that the difference is significantly different from 0, and therefore they are the same, and that the difference is 0. Okay, either one you can say at that confidence level. So now you are making probabilistic statements, and so like that. Okay, so now here's the thing. I don't know whether this is a different example, but we take these numbers. And the question is now we are extending another thing. So why 0? Suppose the question is not about 0. The question is about 1. Is the difference 1 between the two processors? Now look at the confidence interval. Since 0 was included, we said, well, it could be 0. Right? Now 1 is included too. So the difference would be 1 as well. Right? So the answer is yes. The difference could be 1 as long as you are 99%. Okay, I could be wrong at 9.1% of the time, but So the thing is, in this range, we can't say much. We cannot differentiate anything. Outside this range, we are sure that that the error is only 0.1%. Sorry, the error is only 1%. So the confidence interval, anything in this range could be possible. The sample mean could be 1, it could be 0, it could be -1, it could be +3. Right? That's all we are saying. We are saying that this population mean is somewhere between -1.21 to 3.27. All right. So here is the homework. For the exercise 12.11, regardless of what the data is, you have to find the 10 percentile and the 90 percentile from the sample. So this is not the confidence interval. This is just calculating the percentiles. Sort the numbers and calculate the percentile. Right? Then you get the sample mean, sample standard deviation, and you get the confidence interval. So they are different. Percentiles are different than the confidence interval. And then the question is, what fraction of programs make less than or equal to 25 IOs? What fractions of programs? This you can just read from the data. You can just calculate how many programs made less than 25 IOs, and that will give you the percentage right there. What is the 95% confidence interval for the fraction? Now this is something that we have not done. So this homework you cannot do until we go to the fraction. So just hold on to that one. This one, if we don't get to that fraction thing, then this will not be due. Now what is the one-sided for the mean? Okay, so these two things actually, one-sided we are going to do just in the next few slides, and the fractions a few slides after that. Maybe I should move the homework after those two things, but right now these three things you can do.